Hello, everyone. How are you doing again? All right. My name is Janet Carr. I am the moderator today, and today we will have a panel about polymer additive manufacturing technologies for transformative manufacturing. So I'm going to bring up a couple of our speakers today. For example, we have Callie Higgins, who is the co-project leader of,
Photopolymer additive
Polymer
manufacturing.
manufacturing at the National Institute of Standard and Technology, NIST. Do you want to introduce yourself as I am bringing up other folks onto?
Yes, absolutely. So I lead the photopolymer additive manufacturing project at NIST, as Janet so kindly mentioned, and that means leading all of our industry interactions and also our fundamental research that we're doing in this space. And really, the work that we do is essentially exists to try to serve U.S. commerce and further this field. So we're here to serve you.
All right. How about you, Shelby?
Hi, everyone. I am with Raise 3D. I am the business development manager here. And with Raise 3D, we are the leading manufacturer of industrial grade 3D printers. So we have exciting technology that is coming out.
Fantastic. And how about you, Aubrey?
Hi guys, I'm Aubrey. I am in my second year as a materials engineer at Azul 3D. I am very early in my career. So before coming to Azul, I got my bachelor's in chemistry and my master's in material science and engineering at Rochester Institute of Technology, where I studied the formulation and optimization of self-healing 3D printable photopolymers. And now that I'm working at Azul, like I said, I'm a materials engineer. However, I do wear many hats since we are kind of a startup environment. So my primary role is to develop low viscosity, unique characteristic elastomer resins that are based on customer consulted part properties. In addition to that, I kind of work on doing total processing for our materials by working with our applications team after parts have been printed, in addition to helping with some additional testing for material part geometry optimization.
Fantastic. And we'll have Amber. Do you mind introducing yourself as well?
Yeah, hi, I'm Amber, and I'm also a materials engineer at Azul 3D. So I work really closely with Aubrey and the rest of our materials team. I got my bachelor's in chemistry from the University of Tulsa, where I did some research in FDM, but also some other areas like molecular modeling and microscopy. And then went to work in battery materials for a little bit, optimizing organic synthesis for a novel battery material. And then I moved here to Chicago to join Azul 3D. So I'm still pretty new to polymer AM, but starting my third year with Azul, and in addition to doing a lot of material formulation, I also focus a lot of my work on investigating what additives can be introduced into our materials to make whatever properties we need to better. And I really enjoy it, and I'm happy to be here.
Wow, we have so many experts on set today. So thank you so much for your time. We're really excited to dig into some of these questions. But if you're in the audience and you do have a question, feel free to put in the Q&A box, and we'll try to get to it during the discussion today. So we actually want to pick on Aubrey Holland first. Where is the future of materials development going?
Absolutely. So first, when you're thinking about the future of material development, you kind of have to think about where the future of the entire field is going, which in the past for several years, 3D printing has been utilized a lot for prototyping, which has been great, but we think that as an industry, we should be moving forward. We should be wanting to be more competitive with large scale manufacturing. Now, to kind of preface this, we do need to consider the fact that additive manufacturing, especially for polymers, cannot necessarily be 100% competitive with traditional manufacturing, as our materials are more expensive and the materials and the processing in traditional manufacturing, such as injection molding, have been optimized for decades now for various industries. However, when it comes to 3D printing, you can't really have a one-to-one comparison for a 3D printed part versus an injection molded part. The reality is they are very, very separate processes. But since there has been so much optimization in the field with traditional manufacturing, it's very important for us to be developing our materials and having value added to the end of our products that are not comparable and unachievable by traditional manufacturing. So the way that we can really go about this with respect to our material development is first considering simply, especially with respect to photopolymers, because that's kind of where my expertise lie, just creating more materials with a vast capability and a vast number of properties, because the reality is where we are right now with respect to our material libraries is very, very narrow. And if additive manufacturing with respect to polymers wants to really get to a space where we can be competitive with larger scale manufacturing, we can't be asking potential customers in the field to compromise on the final properties of their products simply because there's only a handful of materials that actually meet the general classifications that they're looking for their final products. So what this means for me as a materials engineer is I'm going into the lab and I am formulating more complex material properties and things from the building blocks of our materials. So I'm considering the monomers and oligomers and even additives that I'm adding to my resins in order to optimize properties and manipulate the polymer network that we're creating in order to improve things like the elongation and the tensile and the tear strength, etc. So we really need to be considering expanding our library so that way it can be more appealing to industries that 3D printing wants to enter. On top of that, in order to be truly competitive with traditional manufacturing, we need to also be considering our secondary properties. So a lot of polymers that are used today in traditional manufacturing have, like I said, optimized UV resistance. They have better temperature properties. They can have a very low compression set. And the reality is if our, filaments and thermosets, photopolymers alike, cannot compete with that, then it's not something that's going to get picked up. So when we are considering this, we really need to ask ourselves kind of what additives are we using? And again, what kind of chemistries are we using to optimize the materials that we're making in order to be competitive with the resins that the materials are already out in the field. And then finally, we need to be considering not only our materials and improving our materials as much as possible to meet these expectations, but as an industry, we need to be asking ourselves, what values can we add to our materials and to our end products? So value added that we see in additive manufacturing includes the customization of 3D printing, the unique geometries that can be attained, consolidating the manufacturing process and minimizing the supply chain. And all of these things need to be considered with that material development in order to make additive manufacturing preferable to traditional manufacturing, regardless of the increase in cost.
That makes a lot of sense. There's so many factors when it comes to photopolymer production. It's quite interesting because you have Azul 3D here, but we also have Raise 3D. In terms of Raise 3D, Shelby, what technology is new here? Because most people know Raise 3D as like FDM technology or pellet production technology. What value do you guys bring compared to what we just talked about now?
Well, it's great to be here with such a great panel of women. I'm excited to be here, excited to share some really great things that have came out that the end of last year. So for those that maybe not know who Raise 3D is, we are manufacturing of printers, industrial printers, and professional FFF 3D printers. And today I'm going to touch on the Pro 3 printer. And so the Pro 3 printer is a large format FFF printer with a build volume of 300 by 300 by 600, which 605 millimeters, which is pretty big. And it's used for fulfilling large scale production and multi-size rapid prototyping. And so what we see is I ask people, what is the biggest disadvantage, with 3D printing and the industry? Well, time is money. We see that it is timely to make these prints. And so our R&D team came together last year and they came out with the Hyperspeed upgrade kit that is now proven to print 3 to 5 times faster, which is huge. They updated the hardware, they updated the filaments, the software. When it comes to high-speed printing, the role of the hardware is fundamental in delivering high-quality printing results despite the extremely high printing speeds. With the Pro 3 printer, strong and stable frame ensures high dimensional accuracy and excellent surface quality, withstanding the effects of extremely high acceleration and high speeds. Additionally, its advanced onboard processors can handle over 600,000 steps per second and implement the active vibration cancellation algorithm on the Pro 3 3D printers. Now, what else is super important is the filaments. That is a big component in this Hyperspeed upgrade kit. And with the Hyperspeed line filaments, they're designed to withstand the higher speeds and yet still maintain that quality. With the optimized and balanced molecular weight, the Hyperspeed ABS and Hyperspeed PLA have higher flowability and lower heat capacity. Melting and cooling are both faster. And as a result, we see that the surface quality of parts printed using the Hyperspeed filaments is smooth and most of the sharp details are maintained. The Hyper's core line filaments can also be launched and designed for industrial and in-use parts production, as well as heavy-duty applications. So high-speed composite filament, tailored fiber distribution, smooth surface finish, and less nozzle abrasion. Now, with the software, Race 3D is always constantly developing slicing software for its users to have at the most available need and to make the most printers potential. So a question that we receive a lot is, why is this important? Well, this is huge. To be able to print 4 times faster, you're going to see big 3 things that are going to happen. Your prototyping is going to be 200% times faster. Huge. For small batch production, it's going to be 200% faster. And prototyping, small batch production, and in-house supply we see is 1,000% faster. So with the Hyperspeed upgrade kit, your Pro 3 series becomes capable of hyperspeed printing, which we see is a game changer in this industry. And it is really grabbing a hold of a lot of our customers that 3D print for aerospace, for medical, this is huge. This is huge. And we are on top of this technology, and we are excited to be on top of it and share with y'all today, the women of 3D printing. And we are excited to be here. So thank you.
Yeah, with all this new polymer technology that's being built, and also marrying with the hardware becoming more mature in processing this material, and then adding the layer of software, it's really exciting to see how additive is accelerating the polymer space. On that note, Amber, what is back when we were doing the discussions before, you were really focused on continuous 3D printing. How is that, angle different than Raise 3D or what your colleague Aubrey mentioned earlier?
Yeah. So Shelby was so right to say that time is money. And so I'm really excited to share how we're taking that into account in our work. So if we are working under like Aubrey's assumption that 3D printing should move beyond prototyping and towards large scale manufacturing, we need to prioritize speed and volume in order to realistically compete on that playing field. So yeah, if we want to manufacture a lot of things, we need a large print volume and we need to be able to print quickly. So the reason that in my work we use DLP, first of all, is because it's shown to be one of the fastest ways to print polymers, because you have your vat of resin and you're curing an entire layer at once. And we make that even faster by printing continuously. So rather than printing a layer at a time, lifting and resetting, which adds time to the process, we are able to continuously pull the part out of the resin as it's curing. And that's faster. It saves a lot of time. The reason we're able to do that is because in our printers, we have a mobile fluid layer that runs along the bottom of our vat. It's transparent, so the resin can still cure. It doesn't interact with the resin, it's inert. And what it really does is it keeps the printed part from adhering to the bottom of the vat. So that's why we don't have to continuously lift up and down and print every layer separately, and we can pull the part up. Another benefit to the liquid mobile layer is that it actively cools the system. So without active cooling, the polymerization is exothermic, and it can very quickly heat up your vat and your printed part upwards of 150 Celsius or even larger, or even for larger parts, the problem can get worse. And having your vat that hot can cause warping, cracking, loss of resolution. So by cooling our system, we gain a lot of speed there too. There's no limit to how fast we can. There's a limit, but we're maximizing our print speed. And in addition to that, because the system's being cooled, we are minimizing our size limitations. So we can expand our print area much bigger. So we've maximized, I'm so sorry. So we've done that. And on top of that, we also formulate primarily low viscosity resins. And that means that the resin is able to flow much more quickly in to replace the cured resin of the printed part, which also adds speed. So we have our high speed, we have our high volume, and we've shown that we can do this with all types of resins, rigid, durable, elastomeric, with no oxygen sensitive issues. And the reason that the industry would benefit from this technology is because the combination of that high speed and high scale gives a high throughput, which you want for industrial manufacturing. And then in addition, we have the other benefits of 3D printing of little waste, and the ability to quickly change designs. Mm-hmm. And what really excites me about this technology is how the printers are able to work really well with the material and with the complex geometries to do what traditional manufacturing can't.
Speaking of complex geometries, Callie, what are applications of these new technologies you've seen on the market that you're excited about, that you maybe want to hear more from some of these speakers?
Yeah, so I think, I don't know if anybody in this community and anybody here that is doing these kinds of work, but 3D Systems has done a fair bit of work in the space. But at NIST, we have one of our missions is to serve, as I mentioned, U.S. commerce. And so everything that we do is to enable new technologies and development of them and making them actually useful going forward. And vat photopolymerization, I did my PhD in all of this, and specifically for regenerative medicine. And it's it has drawn me so much because it is the only technology in existence, like literally in existence, that allows you to engineer at the length scales that are relevant to cellular structures. So at that micron scale lengths and lower. So you are only limited by the light that you are using. And it's because you can build up, molecule by molecule. And this is incredibly useful, as I mentioned. So you said, what are application spaces for this incredible technology? And one area that we are working with some collaborators on is regenerative medicine. And I think what's most baffling about this field is that not only is it, improving certain areas or providing this really cool complement to other traditional technologies, but it's enabling fields. Like, it is enabling a completely new field of regenerative medicine. We never on the face of planet Earth have we been able to build tissue specific to the patient. And that is exactly what this is enabling, which is boggling. And honestly, if someone had asked me at the beginning of my PhD if this was something that would be possible, I'd say, yeah, theoretically, sure. But I would never have guessed that it would be something on the horizon. And that is what really truly is on the horizon, is being able to build tissues and organs that are specific to the patient, so that we don't have to worry about rejection, and enabling that kind of the transformation of that whole entire field, which is really what gets me out of bed and excited every morning.
That's amazing. Aubrey and Amber and Shelby, are you seeing this as well in the industry, or what are other applications you're seeing that's knocking your socks off?
I think some applications in the industry that are really interesting is just a matter of how we can kind of reimagine where we're going with 3D printing. So as I previously, and Amber and all of us have been kind of chatting about, is, having this material and having various geometries and just incorporating new materials into the field with different geometries is allowing us to really tap into a space that has not been super explored yet, because this is an entirely new industry, and it is kind of something where our imaginations just kind of can lead the way a little bit. Of course, we always have guidelines and stuff with respect to the technologies that are currently available or the materials that have already been developed and everything. But, it's a matter of looking to the horizon and saying, what do we want? Where do we think we can go? And then getting to be able to explore that space. I know that's something, as a material formulator and developer, Amber and I really, really get to enjoy every day, just going into the lab and seeing what we can do and what is possible. So of course, like with Azul 3D, and it sounds like with Rise 3D too, we do want to prioritize making larger scales and making things faster and making things more competitive for prototyping and manufacturing. But it's also really just an exciting space to explore as well.
Yeah, for sure. I meant being on top of this and really seeing how the industry is growing is just very encouraging. And it's exciting to see, every company really having its own niche and being able to display throughout this whole entire conference what they are doing and how it can really change, the world. I mean, it's great. It's great.
Oh, and you're muted, Janet. Oh, Janet, you're still muted.
Yeah, I was wondering, Amber, any cool applications you've seen Azul 3D explore? Because I know Azul has done quite interesting things on the consumer sector, but are there other sectors that are worth looking into that you guys are paving the way for?
I don't know if I can talk about what we're doing specifically, but just for me personally, what has been really exciting to see is how 3D printing has been incorporated into robotics. It's just like, to see these parts in motion, I just think is super cool. What do you mean by robotics?
I want to say something I just thought was really a great comment you just said. So recently we were at a show, and there was a company from Germany I met this machine, this robotics machine was probably $1 million at least. It was amazing. And they get here and their bracket is broke. And so they have to have the bracket for it to work, the arm to work. So they came up to us and they said, hey, can you 3D print this in a few hours? And we said, absolutely. And we got the file. We printed it on our RMF500. I think it took an hour and 30 minutes. And it saved the show. Like, it's just amazing how much this 3D printing, how it corresponds with so many other things. So it's just exciting. I loved what you just said, Amber, and how dynamic it really, really is, you know?
That's amazing. 3D printing saves the day. It should go all over the news. But regarding, you know, more tactical things, we actually have a question from our audience. Don Clark wants to know, do you have or are you working on developing photopolymers that can achieve strength nearing those of nylon?
So this is a great question and kind of brings up a couple different things that we've really been considering at Azul 3D, and the direction of kind of how we think about materials should go. So one major problem that we do see sometimes when discussing you know, different materials with customers and in general as an industry, and Amber can probably hop in on this too, is the fact that a lot of the time you are talking about materials and using, you know, we're saying nylon like or ABS like, especially with respect to thermo sets. But with respect to 3D printing, we've found that a lot of the time your material properties are entirely dependent on your final product that you're getting. So a lot of the time we'll see that you can have a material that is characterized by, say, ASTM standards to, you know, on a spec sheet, meet the expectations of what nylon should look like. However, after it's been 3D printed and integrated into a specific application, we're seeing, especially with lattices that are being developed, that it's not necessarily a one-to-one comparison. Especially at Azul 3D, we are looking into more so, okay, what is the final application, rather than just saying that you want something that can maybe meet the expectations of a previous traditionally manufactured material. We're more interested in saying, what is your application and what are the material properties truly necessary to get to that space? Because when we're making 3D printed parts, most of the time we have some kind of internal lattice structure, and it's not necessarily one thick piece that's being printed. And so, you know, your final property of your material and that you're making should be able to encapsulate, you know, the material properties and the potential that 3D printing unlocks geometry-wise.
That's a really interesting point, and I think that you really bring to the forefront one of the biggest kind of, not issues, but things that we really need to address in this field is that, yes, we have ASTM standards for bulk structures, for bulk materials. So like, you know, things like nylon, like other types of engineering plastics. But those standards, like none of those ASTM standards actually can be applied to 3D printing because of the manufacturing process. And so I'm actually one of the leaders for the materials subsection of ASTM, and that's something that we are actively pursuing and actively want participants in terms of standards participation, because the moment that someone tests something using an ASTM standard and they print a different geometry and all of a sudden it behaves very differently, that could potentially go to, you know, catastrophic failure, and we lose consumer confidence. And the moment we lose consumer confidence, we've lost the field possibly. You know, if there's one catastrophic failure, like that's a news article and that can have huge consequences. So understanding what the I think really helping the customer understand what the specifications truly are that they need. Like, what are the properties of Teflon that you really want to capture? And then how do we engineer the 3D printed material to have those? So that includes the geometry itself. So you can engineer the geometry itself to have those properties in addition to the material. And so there's a really interesting space that we get to play in with metamaterials and these complementary composite structures that is so unique specifically to additive manufacturing that I think we need to kind of re-educate the public in terms of how we think about materials and their behavior.
Yeah, so just to jump in, I think the short answer to are we developing a photopolymer that is nylon-like is we're developing a lot of things. What do you need it to do?
Speaking of developing materials, Amber, how do you approach developing new materials?
Oh, okay, perfect. So we started getting into this. So on my team, we have a approach to material development that I really like. It's very like open world and very creative, and there's just so much space to play within. And essentially what we're doing is an application-based approach, and that's what we were just talking about, and that's what it sounds like, where we are faced with a potential application and we are going to focus our material formulation toward that end goal. Like a lot of material manufacturers might work the other way around, where they have a finite library of materials, like, you know, several elastomers, several more rigid materials, and they will work to apply that existing material to the application. And we're looking at it sort of the other way around. So yeah, like as opposed to working towards being ABS-like or polypropylene-like. So we're working with the goal and the general idea of our materials should be as customizable as the complex geometries that 3D printing offers. So we're at Azul on my team, we're doing that in a couple different ways. So we are working with thermosets that give us a lot of UV resistance and corrosion resistance, and also offer a lot of strength, especially via our continuous printing method, because the polymer chains are able to build three-dimensionally. And so you could have consistent properties across all three axes. And thermosets also just give a lot of customization space to play in, and that's our whole goal. Another thing that we're doing is, rather than looking at our materials as a finite catalog of offerings, we are thinking of it more as a customizable, infinite sort of branching family tree, where if we are faced with a new application, we might tune an existing material because we're very used to tweaking properties, or we could even build a new material from the ground up as needed. And like we were just discussing, it's really easy to be bound by ASTM standards. But yeah, we're trying to go beyond that and look at, you know, especially what secondary characteristics does the application need, like a low compression set, or maybe a high impact resistance, or UV resistance, chemical resistance, and also putting a lot of focus into those. And we also focus a lot on how, again, material and geometry work together. Like you could have two of the same lattice made of different materials, and they would feel completely different. And you could even have two of the same lattice made of the same material, and they could be made to feel completely different just based on the processing. So that's our approach, is that 3D printing already offers so much customization, and we are going to expand that even further with our material catalog. And that's for the ultimate goal of 3D printing being a real player in manufacturing. And so we think to unlock the complete potential of 3D printing for manufacturing, we need to make everything as customizable as possible. So just freedom.
Yeah, and Callie, since you come from the standards world, do you take a different approach? Do you agree, disagree? Just curious what you think.
I mean, I kind of come from all of the worlds, I think, standards and technology. So I hopefully can have a little bit bigger picture. I mean, I think that I completely agree with Amber. I think that there's a huge component in the design. I mean, it's designed for additive manufacturing. You design your structure for this process. Like, it's not like you can't apply the same mindset of a traditional manufacturing or of a traditional material, as I mentioned. And I think that to the point, in terms of, like how these materials behave and trying to expedite the speed in which these are manufactured, like Shelby and Amber so eloquently described how important it is to go fast. But I'm kind of interested, and kind of posing a question to you guys about how, in all of our collaborators, the number one thing that they have that's the roadblock or the bottleneck is post-processing. It's not the actual printing part. It is the post-processing that requires the most time. And so I'm curious to know what you guys think, like how that can be expedited. Because, obviously, at least for VAT photopolymerization systems, there is a very important critical step that requires you to remove any excess monomer, because that is, kind of by design cancerous. So we have to remove those materials. But then also, when you have a technician handling them, we have to ensure that they're not exposing themselves. So there's a many layered process that is required. And so I'm curious to hear what you guys, your thoughts are on how that can be expedited or improved or modified.
So from kind of a photopolymer perspective, a lot of the time it is about kind of going back to the chemistry, including, all of the different components, the monomers, oligomers, and the additives that we're using in order to make sure that we get our materials, coming off of the printer as reacted as possible, in a way that can still allow us to manipulate properties before going through its final post-processing phase, so that way you can have your final product. So a lot of the time, we're considering kind of, what kind of photo initiators are we using and in what concentration, in addition to looking at the reactivity of the materials that we're using, to kind of go about that approach. I don't know if Amber has any more to add to that.
I would just say, yeah, I think we're very, very conscious of post-processing time and have a whole team of people who are working to optimize it. And it is also just as customized as every other part of the printing process.
Right.
And to also kind of go with that, it is about kind of looking at the, the SDS sheets to see kind of what are the potential hazards of the materials that we are putting together in our resins and things like that.
I mean, that's it's an interesting point then, that was in the back of my mind. One of the biggest things that's happening in VAT photo right now, and the biggest hurdles, and which is scaring the bejesus out of everybody, is that a lot of the photo initiators that we're using are blacklisted now in Europe. So TPO is definitely blacklisted, and it's like probably one of the most ubiquitous photo initiators in all of additive manufacturing for photo. And like, that's pretty terrifying. And so if you can't even use that in Europe, like what is the United States going to do, number one, but what other alternatives do we have? And then also fluorinated materials are also like definitely on the blacklist in a lot of countries. And, as Azul 3D uses a fluorinated oil as their layer, I'm curious to know what you guys are doing, because I know that like that's possibly going to be a big hurdle too with these incoming kind of regulations.
So I'm not sure exactly how far we could get into something like that technically. But I do know that, with the next iteration of printers and everything coming, our hardware team is being very conscious of how they are developing, our materials to improve the printing qualities and our printability of our materials. So, Yeah, and with that, it's one of those things where when we are considering what we're putting, it is a fun space to be in because we get to explore kind of what we're adding, and then being conscious of currently what are the issues that we are facing right now, and what are the problems with what we're currently putting into our photopolymers and stuff. It's really important, and we're lucky enough that the industry is young enough that we can really take a step back and consider the things that we're putting into our resins and our materials in general.
Great. I just saw a question in the box for me. It says, how is the Racer D RMF 500 able to properly print nylon-based filaments without a heated chamber? And so this is an industrial printer, the RMF 500, that is recently, as well as the upgrade kit, we just released the RMF 500, which is really exciting. And so the RMF 500 currently designed for PA12CF, which is a nylon-based material. And this is integral because with what I spoke with before about the upgrade kit, this will be put on the RMF 500 as well. So we'll see that not only professional printers like the Pro 3, but the industrial printer will also be able to print at those high speeds as well. So thank you for that question.
Fantastic. Okay, it is now 4:21. And we probably have to head over by 4:25. So I was thinking maybe we could squeeze in 2 extra questions, that the top 2 questions that have risen up, but only one person gets to answer. Whoever answers first gets to say what they want to say. Okay, we have Idalina that's asking, do you see the market of thermoplastic biodegradable polymers or recycled raw materials for 3D printing? Do you have experience or requests from customers about this issue? Amber, you nodded.
Yeah, I think I can speak a little bit to that. I think sustainable practices are constantly being talked about. And I guess just from the perspective of the work I'm doing, that's why it's so nice that we have so much leeway and so much creativity in our material development, that when and if we're approached about something like that, we have so much experience with playing with materials that we can do the work to see if we can make that happen. But definitely I see a lot of things, a lot of interest in biodegradable and recyclable products.
Fantastic. Second question. We are looking to add PU to our SLA workflow. What additional steps in the workflow are required for PU versus traditional SLA resins?
What is PU?
I think it's probably polyurethanes.
Okay. I'm like, what are they referring to as PU?
From my perspective, I don't personally work with a lot of polyurethanes, so I'm not entirely positive the best way to answer this question.
Okay, no problem. And oh, this is fun. Are there any top secret NIST technologies Callie can share with us?
Oh, we're so top secret. Come to campus. I'll show you everything. We actually do have a lot of really awesome creative collaborations. We have so many NDAs, it's silly. But I can't really talk about a lot of the work that we're doing, but we are working to fabricate lung tissue, which is, I think, kind of insane. You can wash the perfusion of oxygen into blood. It is boggling. I can't even, our collaborators, I just look at their labs in awe. So we're just excited to be able to provide a lot of the fundamental science arm of it.